Well, now that we are getting into 9.3 and 9.4, we are now getting into the concept of a definite integral instead of an indefinite integral. So up to this point, we have just found what we call an indefinite integral, which is to integrate a function like this, and then just get a general expression for what the integral would look like. But when you do a definite integral, you're assigning real values to your function, and you're actually solving for one specific number or a specific value instead of just a general expression. So you're going to get a quick background on where this comes from. I would encourage you to look up more. If you've already taken calculus, you've already seen this. But when we talk about a definite integral, so we are looking for the integral of something like this from, let's just say, from 2 to 16. So we're identifying a lower and an upper boundary. What you're really doing on that, and where this comes from, is you are finding the area under a curve. And so if you were to graph this function and we were to find the area under that curve between the x-axis and the function itself, well, how do you find an area under a curve that has a constantly changing slope as you go on? So what this came from was old dead mathematician guy, Riemann, said, well, let's create a bunch of rectangles under that curve, and we will just add all those rectangles together. And so if we were to form a bunch of rectangles and find the area of those rectangles and add them up, we would come pretty close to getting the area under the curve. But notice there are some gaps here. And so whatever we come up with right now is going to be a little bit less than the area that we want. This is called a left Riemann sum because we're using the left endpoints of our rectangles. Well, if we went the other way and did a right Riemann sum and used the right endpoints of our rectangles, well, notice on this we would get more than what we want because we have now some rectangles spilling over the curve. So we know it's somewhere between this left Riemann sum and this right Riemann sum. And so the idea was, well, if we create more and more rectangles, this space would get smaller and smaller and smaller. So as we get an infinite amount of rectangles, we get closer and closer and closer to the area that we actually want. So when you are doing a definite integral, that's where this comes from, but you are finding the area under the curve essentially by adding up an infinite amount of rectangles to get that area. I attached another video. I encourage you to watch it. And of course, if you really want a little more background on this, pull up one of those Khan Academy videos on the first fundamental theorem of calculus, and you can get some great depth of explanation on what you're seeing with all this notation. It's really not as complex as it looks. It's just a lot of symbols floating around. So I'll throw out one idea. This was the first principles method that we did earlier this year, which is just where a derivative comes from. So if we were to do the limit as h approaches 0, then you approach a specific number as h gets smaller and smaller and smaller, and that was the whole concept of a derivative. And so now we're applying that idea to show that if we were to integrate that derivative, we get the function, which is the area under the curve. And so here's a little more of that explained, but again, here's kind of the main idea that we're getting at in this video, is we are now finding the area under the curve from a lower bound to an upper bound to get a specific area. So because we are throwing in specific boundaries, we now go from having this look, which was an indefinite integral, to a definite integral. So we're going from 0 to 16. So we are putting a limit on this to get a specific area under the curve instead of something like this, which would just basically say it goes on forever. When you do an indefinite integral like this, you must throw on the plus c, because again, we're creating that family of functions, and that constant could be anything. But when you do a definite integral, and you can follow the math on this and see where this came from, but the c's would cancel out, and so you do not need the c when you're doing a definite integral. You'll simply come out with one number. Generally speaking, we are going to integrate this function. Once we get the integral, we're going to plug in a 16, we're going to plug in a 0, and we're going to subtract those two answers. So we're always doing this minus this when we get to our integral portion. And so we're getting the area from here minus here, and that's what gives us the interior portion that you see on this. So let's go through with a couple examples. And again, I'm not going to talk through every one, so please feel free to pause this at some point and try one on your own. But the overall idea here is to integrate from 1 to 3. So we are finding the area of this curve. If you were to graph this, and you can graph this on your calculator, we are finding the area under that curve from where x is 1 to where x is 3. And so we are putting limits on the area that we want to find. So essentially all we have to do is find the integral of this function. And so using what we've done in the past, this is what you would now have as the integral. Notice the change in notation. Once the integral has been found, we no longer use this symbol from 1 to 3. We now use, and it's usually a vertical bar right here, is they just put a vertical line right here and put the limits from 1 to 3 on the right side of your integral, no longer the left side. So once you've done the integral, your boundaries move from left to right, just to show that we now have the integral, and we're going to evaluate this from 1 to 3. So we're going to plug in a 3 for x. We're then going to plug in a 1 for x, and we're going to subtract our two answers. We're going to find the difference between the two. If you plugged in a 3, you're seeing that look right here. If you plug in a 1, you're getting that look right here, and we're going to find the difference between those two answers. Just as you're seeing right here, watch out for the double negatives. So we added those answers together, and this is what we came out with. Keep them separated with parentheses and the minus sign, just so that you can make sure you're safe on double negatives like this one. So here's another one if you want to pause and give it a try. But again, we would put this in a friendly format. This is x to the 1/2 power. We're going to ignore the constant for just a minute while we take the integral. So if we integrate x to the 1/2, we would add 1 to our exponent and get 3/2. We would then divide by 3/2, or you could say I'm going to multiply by 2/3, same thing. Now we can bring in the constant that we had, and so here's the 2. So you could do what they did and save it for the end, or you could filter it in right now and call this 4/3. Either way, it doesn't matter. But once you have found the integral, again, notice now the boundaries have moved to the right side, like you see here. And so now we are going to evaluate this function from plugging in a 9, then plugging in a 4, and subtracting those answers. So here we are plugging in the 9. Here we are plugging in the 4. We are subtracting those two results. And then they brought in the 2 at the end. It doesn't matter. Like I said, you could have done this earlier on. Either way, we should still come out with this as our answer. And then one more, if you want to give this one a try. Again, you're going to put that into a friendly format first. You're going to find the integral, which is this. You're then going to evaluate it from -1 to 3. Or I should say from -3 to -1. So those moved over to the right side because we have now found our integral. And so we're going to plug in a -1. We're going to plug in a -3. And we're going to subtract those answers to get 2/3. So 2/3 is the area under this curve from -3 to -1. Same idea right here, but this one really helps to have a visual aid of what we're doing. So if you were to take this function and graph it, the 1/8 x squared, so on, you would get this parabola that you see here. And if we're going to find the area bound by, they're giving us a couple boundaries. So from -6 to +12. So if I drew in the line x equals -6, I get that vertical line. If I drew in the line x equals 12, I get that vertical line. So we are going from -6 to +12, but we're also setting a underneath boundary of y equals 0, just to show that we are stopping at the x-axis. So this is the line right here for y equals 0. Obviously, if we were to just say the area under that curve forever, that would include all this as well. And so they're giving us the lower boundary so that we know to stop at the x-axis. So again, we are now going to integrate this function. They gave us boundaries from -6 to 12, and so we're finding the shaded area that you see on the right. So if you were to integrate this function, that's what you get right here. So we now have the integral. So we move our boundaries to the right and say we're going to evaluate this integral from -6 to 12 to get the area under the curve. And so we're going to start by plugging in a 12. That's what you're seeing in the first parentheses. We will then plug in the -6, and then we're going to separate those answers with a minus sign. And again, use of parentheses is important so that we can take care of the double negative and get this guy right here. Same thing right here. Again, we're given some boundaries, so x equals 1 and 8. And so that's what's setting up our lower and upper boundary that we're going to find. Keep in mind that when you find the area under the curve, the positive and the negative show where the area is. On the last problem, when the area was above the x-axis, it came out as a positive. But if you have an area below the x-axis, it will come out as a negative. That just shows the position of the area that you're finding. Of course, we never state the area as a negative. We always state it as a positive. So that's what you're seeing, this concept right here. If it's below the x-axis, we're going to throw in a negative for the integral so we can cancel out the negative that we're going to get in our answer so we can have a positive answer. We'd never state the area as a negative. But again, here we are with the original function. We're now going to find the integral of this function, which is this one right here. We have now found the integral. We're going to evaluate it from 1 to 8. So we're going to plug in the 8, plug in the 1, subtract our answers. So here we are, we threw in the 8 minus plugging in a 1. And notice on this one that, you know, if you did the regular integral process on this, you do come out with a negative area, but that's why we threw in the extra negative so that we can write our answer as a positive. And obviously you don't have to write this, you just need to recognize that it's positive and never state your area as a negative. Yes, this can be done on your handy dandy calculator. Even easier than what you see right here. If you have one of the newer TI-84s, the easiest way to do this, and I can help you if you have questions on this, the easiest way to do this is to go to your y equals button and graph this function. So go to y equals, graph this function, and then if you go under calc, go down to option 7 where you'll see the integral, and then you just plug in your lower bound and your upper bound, and you can get it that way. So here's something that is extremely important about this. I'm glad you're still watching. Notice on this one, if I go from -3 to 0, well, part of that area is above the x-axis, and I would get a positive on that. The other part is below the x-axis, and I would get a negative on that. So I need to add a positive with a positive. So to do this, you have to identify that this area is positive, then get the positive version of this area, and then add those two together. If you just go in your calculator from -3 to 0, well, this area right here is 3 1/3. This area is technically -9 1/3, so your calculator will subtract them instead of add them. So really important that you break this up. You would have to do the area from -3 to -2 first, then do the area from -2 to 0. Your calculator is going to say it's a negative, but you're going to turn it to a positive, and then add this area plus this area. So you need to find them separately and then add them together in order to get the correct answer, which is, I believe, 12 2/3. So be very careful on that, but again, all I would do on that is I would graph this function. Once you've graphed it, go under calc and choose option 7. For the first part, you're going to see, and you'll see it, it's even going to shade this for you. It's going to look just like this. After you've done option 7, they want a left boundary, which is -3, a right boundary, which is -2. Hit enter. They're going to give you that area. Do it again from -2 to 0. They'll give you this one, but they're going to give it to you as a negative. You change it to a positive, then add the two areas together to get the total area under the curve.